So we've put a little effort into getting some basic understanding of sort of how geometry and shapes work in 3 dimensions. So the reason that we did this is because we are going to encounter a new kind of function. Okay, and this is one example of the kind of function we're going to work with. So suppose we have a position of an object in 3D space as a function of time. So there's some object and it's moving around as time passes. Right, so our position is given by is determined by some time. What kind of function is this? Well, to locate, this object is moving around as time goes on, and so to locate where, at some fixed time, t, to locate where the point is, we're going to need to write down the x-coordinate of the point, right? But whatever this x-coordinate is, it's a function of time, because different times will produce different x-coordinates. So this x-coordinate isn't just a number, it's actually a function of time, so let's call it x of t. But the same is going to be true for the y-coordinate, because at different locations, or at different times, the y-coordinate will be different, and so y will also be a function of t, and of course z will also be a function of t. Right? So what we get is a function that has an overall function that has 3 individual scalar functions. We could think of this as a moving point, and often we will, but another way to think about this is, we have some coordinate system. Another way to think about this moving point is that we can think of it as a vector going from the origin to each point. Right? So one way to think about what this function is doing is that it is producing, for every time t, it is producing a vector. So this is producing a vector for each time. Right? Since one time gives us 3 different numbers, an x-coordinate, a y-coordinate, and a z-coordinate, we can package those 3 numbers up into a vector. So this is a function that has one input, time, but it has several outputs. In this case, 3 outputs, an x, a y, and a z. So that's the kind of function that we're going to be working with. This is called a vector-valued function because the values of the function are vectors. Okay, so a vector-valued function is a function of a single real variable that produces a vector, and for us it's always going to be a 2D vector or a 3D vector. It produces a vector as its outputs, and we'll write it like this. I'll try to always use a bold-faced R when I'm talking about a vector-valued function. Just this software makes it a little annoying to get a vector hat onto my R's, so I won't do that. But making it bold isn't too bad. So we'll generally call our vector-valued functions R of t unless we have some reason to give it a different name. And it has 3 coordinate functions, x of t, y of t, z of t, or just 2 if we're in 2D. Right? If we're in 2D, we'll just use the first 2 of these. To graph a vector-valued function, we'll just graph all of the vectors. Well, if we graphed every vector for every value of time, that would make a really cluttered picture, right? So actually what we'll do is we'll only plot the endpoints of each of these vectors. So the vectors coming out of this function, we will start them at the origin, right? Plot the vector, and then just record the endpoint of that vector, assuming it is starting at the origin. All right, so for example, let's sketch a graph of r of t equals 0, comma, cosine t, comma, sine t. So this x-coordinate is always 0. So that means that whatever shape this makes, it's always going to live in the plane x equals 0. So, if we do our usual thing of making the x-coordinate go to the right, the z-coordinate going up, and the y-coordinate going into the screen, then the plane x equals 0 is going to look something like this. Okay, so we can generate points on our graph just by plugging in some numbers. So how about r of 0? That's going to be 0, comma, cosine of 0 is 1, and then sine of 0 is 0. So if our coordinate axes are like this, then that's going to be this point right here. So this point right here, that's the point we got from t equals 0. And then we could plug in, I don't know, how about pi over 2, for example. So that's going to give us 0, comma, and then cosine pi over 2 is 0, sine pi over 2 is 1. And so that point is going to be up here. And this is the point t equals pi over 2. And so on, right? You can tell, since we have sine and cosine, we're going to be generating points going around a circle. Right? Sine and cosine trace out a circle. That's sort of their only job in life. Okay, so this vector valued function, its graph looks like, well, it looks like this circle. Okay. For another example, let's sketch the graph of 0, comma, cosine 2t, comma, sine 2t. So again, we're going to be living in the plane x equals 0 because that x coordinate function is always 0. Okay, now let's plug in, I don't know, how about t equals 0? So r of 0 is going to be 0, 1, 0 again. So let me draw our coordinate axes on here, like this. So there. So this point is t equals 0. Let's try, I don't know, how about pi over 4? You probably see what's happening here. 0, comma, and then cosine of 2 times pi over 4, that's cosine of 2, that's 0. And then sine of 2 times pi over 4, that's sine of pi over 2, that's 1. So that's up here. So this point gets labeled, this is the point when t is pi over 4. Okay, and then when r is pi over 2, we get 0, comma, let's see, 2 times pi over 2 is pi, so cosine of pi is minus 1, and sine of 2 times pi over 2 is sine of pi, that's 0. Okay, so that gives us this point down here, and this point is labeled t equals pi over 2. And right, what's happening is this is still tracing out exactly the same circle. Right? Notice that this makes the same shape as our previous example. The only difference is that our t values are different. Right? So these two vector valued functions, they are different functions because, I mean, look at their formulas. The formulas are different. But their graphs make the same shape, right? So this is something that's a little tricky about vector valued functions. We think of them as, often we think of them just as a shape that is their graph, but that is not the whole story with vector valued functions, right? So for vector valued functions, the graph of a vector valued function has the shape of the graph, the total path that it traces out, but it also labels each point on that path with some t value. Right? This is as opposed to like just the geometric shape that is the curve in 3D, which only has shape information. Right? So this in this plane x equals 0, there's this unit circle. Right? This unit circle on its own doesn't have t values labeling each point along the circle. Right? Whereas these two graphs of our vector valued functions do label each point with a t value. In fact, several t values, since sine and cosine are both periodic. So, so we do have to be a little bit careful about vector valued functions. They contain not just shape information, not just the path, but also a location for each time. Right? Each location is labeled with a time value that is the time that you are located at that spot. Now, sometimes this is fine, right? Our original example of a vector valued function was position as a function of time. And for this situation, if we are dealing with a vector valued function because it describes the position of something, we care both about the overall shape of the path and also about the time of each location. But sometimes, if all we care about is the shape, then we won't care about the times at which we are at each location, right? So As we work with these vector valued functions, sometimes we will care about the times and sometimes we won't. And if we don't care about the time at which we are at each location, we'll have to do some careful thinking to make sure that we aren't accidentally getting those times involved when we don't actually care what they are, right? So sometimes the times will be important and sometimes they won't, and I'll try to flag clearly which is which. As a final example for a graph, let's maybe do one that isn't confined to a single plane. So let's graph this vector valued function. We could do this just by plotting points, but instead let's see if we can get sort of a more holistic understanding of what this graph is doing. Plotting individual points is really just a backup strategy in case you can't sort of think your way through what the graph is doing. So what catches my eye about this formula is that the first two coordinates have a sine and a cosine, right? So in the xy direction, this is just going to be going around a circle. Well, actually not quite a circle, because this 2 here means it's going to be going twice as far in the y direction as in the x direction. So if we ignored the z direction and just looked at the x and y direction, this graph would be going around a stretched out circle. In other words, an ellipse. So it would be doing this, right? I'd just go around and around over and over. But as this happens, this graph is going to, the z-coordinate is going to be changing. Right? The z-coordinate is going to be increasing at a constant rate because z is equal to t. So what's going to happen is, right, the shadow that our shape will cast in the xy plane is just this ellipse. So I'll draw it as a dotted curve because this is just the shadow that it makes. So we're going to go around this ellipse, but as time goes on, we're going to move upwards, right? So after a little while, we'll be up here on a higher plane, and then on a higher plane still, right? So we need to go around this ellipse while moving up in the z direction. And so that's going to give us this kind of shape. Okay, so a little bit of a drawing fail. Oh, OneNote decided I was trying to erase something. That's not what I was trying to do. You can see that the shadow that this casts on the xy plane is this ellipse, but we're constantly rising up. We get this sort of, it's sort of a spring shape, right? This shape is called a helix. Okay, it's not a spiral. A spiral is a plane shape, but we're raising up out of a single plane, so this is called a helix, right? So if you can sort of have some more holistic understanding of what these functions are doing and how it fits together, it's usually better to think of the graph that way than plotting individual points. Of course, if you need to plot individual points, you can. As a backup, if you really don't have any idea of what the graph is doing, you can always ask a computer for a graph. So here I have GeoGebra. In GeoGebra, the command to ask it to plot a curve is curve. And then you just type in your 3 coordinate functions. So for our example, it was cosine t sine 2 times sine t, and then our third coordinate function was t. You also have to tell GeoGebra what the independent variable is, and it's t for our example. And you have to tell it what range of t values you want. So let's go from, I don't know, minus 2 pi to plus 2 pi. So there's the graph. Now, we can't see very much of it because it extends pretty far in the z direction. So let me see if I can collapse the z-axis. So there you go. Okay. So you can see it's kind of this spring shape that's going. If we look at it from the top, there's the ellipse. If we look at it from the side, there's us going up at a regular rate. And if we sort of spin it around, you can kind of get a feel for how we're going around the ellipse as we raise upwards.